Thank you, Jorgen, and thank you to all organizers for the invitation in this very, very nice workshop. So I'm going to talk about resurgent series, more precisely simple resurgent series, and more precisely the so-called Z-resurgent simple series. And this is a subspace of all possible formal series in one variable, and it contains the convergent ones. Now, as you may know, the derivations of that algebra of formal series are well known. I mean, the C-linear operators satisfying the Leibniz rule. You have d over dx and any multiple, and that's it.
You mean continuous derivation?
No, it's a theorem that it's automatic in that case. The adic continuity is a consequence of being a derivation. It's a non-trivial exercise. It took me a few years to find the proof in Bourbaki algebra commutative. There is a trick. No continuity is required, but by the way, since you asked the question, if we go to the fraction field, I don't know. If you know the answer, please tell me. Okay, that's a different subject. Now, when we restrict to these subspace, these are subalgebras. They are stable under multiplication. And here we have plenty of derivations, the so-called alien derivations. Here indexed by non-zero integers, here indexed by any non-zero complex number.
I mean, here it's the position of singularity.
Yeah, exactly, that's it. I will define it in 2 seconds. So, in fact, I presented something like that some time ago, and Lee Se from Tsinghua University asked me, since you have so many derivations, couldn't you use them to produce a non-commutative deformation of the product? Although it's just one variable. Usually, maybe we think that to quantize, we need at least conjugate momentum to the configuration variable. Here, it's totally different context. It's a question in algebra. And the answer is yes, we can construct deformation, and to start, before the deformations themselves, we start with the Poisson structures they would induce at first order. So this is the goal of the talk. So let me define the
Is it possible to just repeat what was the definition of like R hat sim?
The definition is now. This is just preliminary remark. I mean, we will define subalgebras equipped with plenty of derivations, and we will play with that. So now let's review the definition. So the definition is due to Ecalle in 1981. So we start with this one. It's simpler to define. So we start with R hat. So this was a twiddle. This is R tilde. We start with R hat, simp, Z. So it is the set of all phi hat being convergent near the origin, such that for any path gamma, so let's say such a path avoiding Z and starting with inside the convergent disk of this convergent germ. So this is disk of convergence of phi hat. So this is the picture. We have phi hat. It's disk of convergence, and we avoid integers, including the origin, but we start in the disk of convergence. And then such a path should be a path of analytic continuation. So the continuation, the analytic continuation along gamma exists and has only simple singularities. So what does it mean? Simple singularities. Let me explain that now. It means that, so you land here at gamma of 1, and you have a germ obtained by analytic continuation. And this germ, now you look at its analytic continuation in direction of integers. And you can go on with the path. So you can go on toward these integers. So let's say we pick one of them, omega. So the point is that for any omega in Z, such that the continuation that we have here can be itself continued, has analytic continuation on the segment, along the segment. So we start from gamma of 1 and we end just before omega. So here that's all integers, but of course if your path happens to land in between, then you just have two such omegas, that's obvious. But then you can go on with a different path and it doesn't matter very much. So the point is that we have this multi-valued function and we are considering all its branches, and all the branches at worst at any integer have a simple singularity, namely the continuation of phi hat at this. So let me write it now, omega plus psi. So now I'm going toward this omega, and here this is my zeta, which is omega plus psi. This should be of the form a constant over 2 pi I psi plus a function psi hat times the logarithm plus a function r of psi with, so C is a complex number, so that's a simple pole, but we authorize also this logarithmic singularity, but psi hat is regular and r as well. So r, we don't care at all about it. It's, by the way, if you change the branch of the logarithm, you modify r. But you do not modify psi hat, and C is well defined, psi hat is well defined. Both of them depend on omega, and of course they depend on the path you have followed to reach this neighborhood of omega. So we have these two interesting quantities, and by the way, to make it more symmetric, so that's a definition, but well, it's incomplete. To make it more symmetric, let me add a complex number a and a symbol. So you see my space here is a subspace of C delta. Delta is the Dirac mass at the origin, if you wish, plus convergent germ. And it's more symmetric. We start with a number and a function, and when we follow this path and we approach omega, we get a new number and a new function. So you see that this space, it's clearly a vector subspace. It comes equipped with operators. So let me introduce a notation. A omega gamma of phi hat. Well, it's a linear operator of, well, now we have A Dirac plus phi hat. So what is the definition? You just discard A. You follow the analytic continuation of phi hat. You go here and you get a number and a function So of course, it doesn't really depend on the path, it depends only on its relative homotopy class. But you need to remember how the address of that neighborhood of omega, how you reach there. Because, I repeat, we authorize multivaluedness very much. And now you see that, so this is a complex number, and this psi hat, what is it? It's the difference of two branches near omega. And each of these branches is obtained by analytic continuation, and by assumption we can go on with analytic continuation, which means that psi hat itself will have the property. And the singularities of psi hat at worst will be simple singularities. So clearly, this is an element of our space. So it comes naturally equipped with these linear operators, A, omega, gamma. And this triggers a definition. For omega in Z, I will choose a very special path, Z star, non-zero omega. Let me choose the path gamma plus plus plus, which means, so I start from the origin. So you notice that, of course, the radius of convergence is at least 1 from the definition. So let's suppose omega is positive. You have intermediary integers, and we follow a path which starts in the disk and which circumvents these intermediary singular points always to the right. So the plus means to the right. So we follow the path like that, and that's it. So, I mean, there are how many omega minus 1 choices? Sorry, omega minus 1 symbols, plus. And this is delta plus. So I insist to define delta plus, you need to remember how you reach there. Circumventing everything to the right. And of course, if omega is negative, then you will go to the right. It means the reverse picture, of course. So that's one thing. And the other one is delta omega. Delta omega is slightly more complicated. It's an average. So here we will sometimes choose plus, sometimes minus, but always going forward. So this is minus, this is plus, this is minus. So you see that you have 2 to the r minus 1 possibilities, r being the modulus of omega, the absolute value. And so for such path, you have a certain number of plus, you take the factorial. You have a certain number of minus, you take the factorial, and you divide by the factorial of absolute value of omega, which is the number of plus the number of minus plus 1. And then you use A, omega, gamma, epsilon, where epsilon is this sequences of pluses and minuses. So this was epsilon 1, epsilon 2, etc. So these are, I hope, clear definitions. Maybe a bit mysterious the first time and not absolutely natural. But they are very nice because there is a theorem. By the way, it's not the first time you see them. We've seen them in Marco's talk, for instance. This week, that was the first time, I guess. Or before getting to the theorem, let me go to R tilde. This was R hat. So we use Borel transform. So the Borel transform goes from formal series in Z inverse. So this X here will be from now on Z inverse. We prefer to deal with non-positive powers of Z. And the definition, well, just for the sake of clarity, so you start at 0 here, but this A0 will go to the Dirac, and then for the other guys, let's say 1, AN, and this is the division by factorial. And we change the name of the variable from Z to zeta. So as a subspace here we have R hat, and we pull back. So the definition is that R tilde simp Z is B inverse of R hat simp Z, and the theorem, and of course we pull back as well our operators A omega, gamma, delta plus, delta, just by making the diagram commutative. So now we have a subspace of formal series with operators, and the theorem proved by Ecalle in this. So it's 1981 is the first volume of the series on resurgent functions.
Is it possible to say like which page of which volume this is in? Because it's always really hard to find things in
Well,
it.
no, the first volume is just 250 pages. It's not, the third volume has 500 pages. I understand your concern. But this one, well, okay, let me give you a nicer answer. Lecture note in mathematics 2153. This is something I wrote. And here, I guarantee from the table of contents you can find it. So what is the theorem? R tilde is a subalgebra So by the way, you see that it contains all the convergent series because their Borel transform are entire. It's a subalgebra. It contains the convergent series. It is stable under multiplication, and for each non-zero integer, we have a derivation. So let me call A this algebra. So this is really a beautiful algebraic framework. And let me mention very briefly the definition of the larger algebra. What about if you don't specify in advance? How do you do that? How do you not specify in advance the location of singularities? It's a bit tricky because you don't want to say in advance, here is a closed discrete set that we want to avoid. You want to allow for much richer sets of singular points. So here is the trick. Where is it? It's the definition of endless continuable. I mean, these guys, phi hat, we can call them Z continuable or endlessly continuable with singularities at worst on Z. And now it's endlessly continuable in the large. So what is the modification? So R tilde simp will be just B inverse of R hat, and R hat without the specification Z will be like this. So I copied the definition over there. All A delta plus phi hat, where A is a complex number, phi hat is convergent near the origin, such that for any L positive, so you fix in advance a length L, and we will restrict our attention to those paths with length less than L. So for such a path, there exists a finite subset, omega L, a subset of C, such that for every path avoiding that set, omega, with initial point in the disk of convergence of phi hat, the continuation exists and has, at worst, on simple singularities. So I repeat, you fix L in advance, so that you fix a big disk and you focus on paths which start from near the origin in the disk of convergence. And well, since you have fixed this capital L, there are points that you must avoid. Probably there is one on the circle of convergence, etc. So you take your path, you avoid them. Well, this was too long because it's L. And now, if you increase L, what happens is that you will discover new singular points farther, but also closer, maybe at the origin, maybe points through which you had passed initially. But now they are forbidden because now we have decided we were authorized to go with a longer length. So that's how you get something potentially dense. I mean, this is clearly countable, but it's maybe dense. Okay. But then you have exactly the same story. But now we have our alien derivations indexed by any complex number because potentially it can be realized as a singularity of one of those guys. Okay. Yes, to be more precise, the definition is exactly the same, except that omega and the intermediary points are not necessarily integer, but that's not a problem because you take any complex number omega, so the modification of the picture is that you have any omega. Well, when you consider paths which follow closely the segment, so you take L to be modulus of omega plus epsilon, there is a finite set to be avoided. I don't care about the other ones, but I care only on those ones. So there are finitely many intermediary points and potentially omega itself, but I can do the same story of paths which circumvent the intermediary singular points to the left, to the right, etc. So the same formula applies and delivers, again, a derivation. That's the claim. So these were the definitions.
So this is not invariant under bipolomorphism?
No, because you lose the... No, you lose the... Yes, exactly, the straight lines. And the straight lines, we like them because in the convolution, I mean, I said it's a subalgebra. The counterpart of multiplication of series is convolution of germs, phi hat, and convolutions, you need the segments and then you deform them. To prove that theorem of stability, you have to work. But yes, the picture is a bit delicate. No, it's in the Borel plane, definitely it cannot be stable. Now, what do I want to say? Examples. Oh, okay. This space is very robust. These spaces, both of them. I mean, not only you can multiply resurgent series, but you can compose them, substitute them into a convergent expansion, invert and take the inverse if the series starts with a non-constant term. And so nonlinear analysis is permitted. And also here, for the sake of simplicity, I deal with simple singularities, but you can also modify the theory to accept more general singularities. But in that case, it won't be a subspace of formal series, it will be, so maybe of the fraction field, this is when you allow for simply ramified series. You accept a polar part of arbitrary order, so it will be encoded in the alien derivative by a polynomial in Z, and that's the good thing to do. I mean, here, okay, now, from now on, we have Z inverse, so I'm just saying that if you accept polynomial parts in 1 over xi, this will correspond to accepting polynomials in Z. But you can also accept Puiseux expansions, convergent Puiseux expansion, and so you can accept logarithms in Z which correspond to something else in zeta. I mean, you can modify according to the needs of the situation. Because the point is that this space, especially, well, both of them, if the singularities happen to be on the lattice Z, you are happy, but if not, okay, you deal with it. But this is the natural habitat for interesting resurgence phenomena, whatever it means. You see, so far there is absolutely nothing resurgent in the story. It's only when you solve particular functional equations that maybe you will observe a relation between the alien derivatives of the solution to a problem and themselves. So it's like functional analysis. You define spaces, and then, okay, you study their properties, etc. But then at some point you have to deal with concrete problems and check that indeed it was a good idea to define those spaces because they contain the solutions, the interesting objects that you want to study. And we have seen examples of that this week. For instance, we had in Maxim's first lecture, we had a simple resurgence package. So I copy the definition, simple resurgence package as I understood it. So for me, it was a collection, a subset xi alpha, discrete, countable xi alpha, a family of formal series. So Maxim's indeterminate was called H bar, and there was correspondingly a collection of numbers for alpha different from beta, and they were supposed to be integers. So that can be rephrased by saying that the definition which was given was essentially saying that they were simple resurgent series. Here, the location of the singularities were not prescribed, or rather, it was through that equation, through the differences. So that was what I understood. And alpha beta I beta if omega is of the form psi beta minus psi alpha, and 0 otherwise.
And no delta functions, yeah.
Sorry?
And no delta functions.
Yeah, okay. I suppose I'm multiplying your series by h. I'm dividing them by h bar, or multiplying them by h bar, and this way, yeah, to make things. I multiply them by h bar. Yeah. Okay. Sorry. Another example. Saddle node ODEs. So that was one of the 5 applications of resurgent functions in 84. And for those interested in references, I have a survey on that in 2008. So details can be filled in that example. At least I know how to do it. And it's about differential equations of a very special kind. So a nonlinear differential equation where you assume that you start with y. It starts like Euler equation, and then the rest is analytic but divisible by x. And there are some assumptions that I don't write. So in that problem, you find one formal solution, but it is accompanied by a sequence and they all belong to R tilde simp Z. So with, well, let's say x is minus 1 over z, so that this is exactly d over dz. So let me use d for d over dz, del. And then they are resurgent. And what is the resurgent?
What was phi 0 and phi 1? I missed that.
Oh, so this is the unique formal solution, and the other ones, the companions. What are they? They are the components of, let me call it like this, so I put a tilde because now I go to the z variable, and there is a parameter sigma. So it's the generating series in which I have incorporated exponentials. So you see, this is a trans series. I have my exponentials going this way. And this trans series is the general solution containing one free parameter, sigma. And here you have this beautiful equation, delta of alpha minus beta phi alpha is beta c alpha minus beta phi tilde beta for any alpha at least beta, well, larger than alpha is larger, at least beta minus 1. And this is non-negative, and, well, sorry, they must be different. Well, alpha can be equal to beta minus 1, but it cannot be equal to beta. Yeah, we must skip that one. And so the C's here, so this is a collection of numbers, complex numbers. I mean, and they have no reason to be integer in that problem. But, well, it's funny to have this reminiscent pattern. And there is, in that context of the analytic saddle node, there is a notion of analyticity. So these CMs are not exactly the Stokes data. I mean, you can call them Stokes data, but they are related through exponentiation. In fact, here we have a derivation. So these CM, we must rather view them as coefficients of a vector field. So there is a vector field in that problem, which is sum of Cm sigma m plus 1 d over d sigma. So it's a vector field with respect to the trans series parameter. Well, there is one to the left, to the right, and there is one to the left.
Is it this Patou Ecalle Baronian theory? You want to explain or not?
It's a sub-problem. It's a part of it, absolutely. And of course, this one, you know, it's exponential. I mean, this is a composition by sigma goes to sigma plus c minus 1. But this generating series might be divergent. Still, it's exponential. So the flow of this formal vector field happens to be convergent. So this is the analyticity phenomenon in that context, to use your terminology. And in fact, a third example would be Ecalle-Voronin theory, where you have beautiful formulas. It's a problem in which you have, I think I have no time for that, but, well, just for the fun, in that problem you have one formal series phi, which satisfies such equations. So here you notice, I didn't say it, but the CMs are just for m equal minus 1 or plus 1, plus 2, etc. In Ecalle-Voronin problem, which is more general than this, the omegas or the m's are any non-zero integer, and you have such formulas. Here you have this minus Cm exponential minus m phi. And the analyticity is manifest in the fact that, again, although these coefficients are not bounded geometrically, when you go to the delta plus, you get new numbers, Sm, and these are the Stokes constant. I mean, here, I forgot to say the coefficients of the time one map of the flow, these were the Stokes coefficient. And here, similarly, when you go to delta plus, you get such formulas. And now it's true that Sm is, so the good viewpoint on Sm, it's a pair of Fourier series. So in that problem, yeah, I'm cheating a little bit. You have a 2 pi Im, but you can rescale it probably, and then 2 pi I is 1, and then you have this, and you have that. So this for m positive, this for m negative, well, the same one. And for m positive, this is good for real part of z larger than something. And this is good for real part of z negative enough. So you have convergent Fourier series. And that's important to remember that especially the delta m plus is naturally associated with the homogeneous component of an operator. So in fact, it's good to think of delta m plus, which is this operator. So maybe I will explain that now. I mean, you can rephrase everything using these operators, and if you know the problem we are dealing with, they are really useful. So these are called the dotted alien derivations, and the dotted alien operator delta m plus dot. I'm sorry, I have no time for that now. Let me explain rather this story better now. Okay, well. Anyway, I want to deal now with derivations of let's focus on the case of Z-resurgent simple singularities. And we will also use trans series. I mean, we've seen an example of trans series occurring naturally in the saddle node problem. So these are resurgent series, and these are resurgent trans series. And you can view that as a completed graded algebra So if you use that, and if you use these notations, so now you see that this notation with the dot makes sense in the algebra of trans series. So this, you can view it as a subalgebra of all trans series, I mean formal series in exponential minus z, whose coefficients are formal series in 1 over z. And so this is again a subalgebra. And now it is here that our delta dot acts, or delta m dot plus. And they are homogeneous. They have a degree exactly minus m. Or there is a kind of a conflict here. Degree omega. I mean, it maps, the graded guys of degree m are mapped to degree m plus omega. So because they have this property, the exponential of the sum of dotted alien derivative. So this is well defined, and you find indeed the sum of the dotted L in operators delta plus. So in fact, this is the explanation for the funny definition. I mean, these funny coefficients directly come from extracting the logarithm of that. You remember the definition was quite simple. Here, always turn to the right. And here, why did we put this funny coefficient? Just because we took the logarithm of something. Okay, so we have these derivations. We also have the derivation d, which is d over dz, and it leaves invariant all our spaces. D over dx would not leave them, and because d over dx would spoil the simpleness of singularities. But d over dz is good.
Sorry, can you remind dotted and undotted? What's the difference between them?
It's the graded version. So you put the exponential. So in the trans-series algebra, we have this grading by the exponents in the exponentials, and so this is it increases the order by omega. So it's good to know that del does not commute with omega, but the commutator is just omega delta omega, and it does commute with delta dot. So now we want to play with these derivations. So, we want to play with them. What is the Lie algebra they generate under commutators?
Delta and delta dot, this is no commutation relation, yeah?
The commutator is zero.
No, between delta and delta dot.
Oh. Delta and delta dot. Yes, they commute. I mean, by definition. That's a funny question. Delta and delta dot. Yes, delta acts. I would say they commute because by definition, these exponentials are inert.
Just exponential, it's kind of
Yeah. I mean, it's linear with respect to the exponentials. So yes, they commute.
Okay.
Yeah. Yeah. And I was puzzled because I never considered simultaneously delta and delta dot. Yes. But you're right. I mean, why not? So what is the Lie algebra generated by these ones under commutators?
Yeah.
What is the associative algebra they generate? So here we have a very strong theorem proved by Ecalle. And again, in my survey, you will find the details. It's a freeness statement. So let's consider, so let's use omega. This will be our alphabet, non-zero integers. Omega underline will be the words on this alphabet. And so when you have a word, omega underline, so it's just an ordered collection of numbers. We define delta omega as the composition in reverse order. So composition of derivations is no longer a derivation, but it's a C-linear map. And the claim is that any finitely supported family phi omega. So for every word I give myself, for almost every, so I give myself an element of A, almost always 0, but not always. So any such family gives rise to a non-trivial operator. The sum of phi omega delta omega. Okay. So I take all these, this combination, it's a linear combination with coefficients in A. And this is non-trivial, and so it's a non-trivial operator unless, of course, the family is trivial. So let me call phi the family. Let me introduce the notation phi bold-face delta for this shorthand notation for this big sum. So it's a big sum because it's potentially over many, many words, so in many languages.
Just free algebra, basically.
Exactly. That's the free. Well,
Is a set, yeah.
it's a free C algebra, but with coefficients in A because it's not exactly an A algebra because the multiplication operator by an element of A does not commute with phi with the so it's a free A module. It's a free associative C algebra. So I don't know how to say it. I mean, it's very free.
A multiplied by 3 on the left.
Yeah. Okay. You know that better than me. It's very free anyway.
There is one question. I think you mentioned it, but so the delta omega i's, do they commute among themselves?
It follows from the statement that the answer is no. Example. Delta omega 2, delta omega 1 is a non-trivial operator. And delta omega 2, delta omega 1 minus delta omega 1, delta omega 2, these are two different words, so that's non-zero unless, of course, omega 1 is omega 2. So that's a particular case. I mean, coefficients 1 for this word, coefficient minus 1 for that word. This is a non-zero family. The result is, I mean, the map here is injective. That's the statement. And of course, this one is a derivation because it's a commutator. So yes, we have a free associative algebra in...
No, it's a tensor product of vector space A multiplied by free algebra with infinitely many generators. That's it.
Vector space A, tensor product with the free algebra over omega. Over omega. But I mean, by the way, the same statement is true with C if you go with, instead of taking... Yes, you can allow. So you have a huge number of operators and of derivations because among them you have many derivations. So when is it, by the way, that you have a derivation? It's a Hopf algebra, absolutely. Absolutely. And yes, that's the trick, to recognize among them the derivations. So that's an addendum to the theorem. Well, before the addendum, a definition. The collection phi is said to be alternal if whenever you have two words non-empty, of course the empty word corresponds to the operator identity. Here the collection is alternal if on the empty word you have 0, and whenever you have two non-empty words, this sum over all omegas obtained by shuffling the two words. You know, you have two words and you can shuffle them. So let me put here a shuffling coefficient, which is 0 whenever omega is not obtained by shuffling, and which is, it counts the multiplicity, it counts the number of permutations which do realize the shuffling when omega is indeed a shuffling. I mean, this is just, it's very natural because when you compose derivations, you don't get a derivation, but you get something which satisfies and modify Leibniz rule. And the modification is the following. We compose these derivations, and here you have the shuffling coefficient. So it's not a surprise that by duality, if we impose this condition, so this is a lemma in algebra. So since we have that, we get an addendum that if my family phi is alternal, then my operator is a derivation. And in fact, it's an if and only if, due to the method of proof, and in fact, it's equivalent to saying that it is a combination of commutators. Here is the formula. You divide by the length of the word, and then you have phi omega times the commutator, the iterated commutator. Delta omega 2, omega 1. So yes, it must be a derivation. Good. So we have really a lot of the, now at the level of the Lie algebra generated by them, it's a free Lie algebra over the alphabet. And again, there is the story of the tensor product. Because, yeah.
You guys mentioned Hopf algebra. Can you comment on this? What's the coproduct?
This is
the coproduct. And the coproduct, I mean, if you coproduct of that, the co-law, I mean, yes, the coproduct of this operator is sum of these d alpha, d delta beta with this coefficient. Well, see my survey in 2008. I dwell a bit on that. In fact, we had a very nice collaboration with people in algebraic combinatorics. So that was my first contact with Hopf algebra, I must say.
It's Hopf algebra or commutative algebra A. Yeah.
Yes, it's so you get something which is co-commutative but not commutative. And okay, if you like that, have a look. And the proof is very algebraic combinatorics. It's there is very fine tools introduced by Ecalle to deal with that. But I must hurry. I'm too slow. Now we can come to the resurgent Poisson structures. Because we have so many derivations, it's a pity not to use them to do something a bit original. So let me write a theorem. Well, if you have questions, you can ask questions. I mean, we are not in such a hurry. I know that we are expecting a nice cocktail, but in 5 minutes. So short question, quick questions are welcome. Theorem. So I'm not claiming it's very optimal. It's my first attempt to do something with these ideas. So let M be integer. Let psi be an element of our algebra, non-zero. Let C be alternal, and I denote it by C because it is scalar. These are complex numbers. It's a family of complex numbers indexed by words with this skew symmetry property involving the shuffling. Oh, it's a pity we don't see it anymore. And I impose compatibility with M. I impose that when in the support of C, we have the sum of the elements equal to M. So this is a notation for. So usually the length of the word, the number of letters is R, and the sum will be S. So here are my data. Then I have a kind of bivector, which is psi del d over dz wedge this operator that we have discussed. So remember, the notation was C boldface delta. So this is d over dz. And the claim is that this operator gives rise to. So let's suppose the family is non-trivial, and then we have a non-trivial a non-trivial Poisson structure. So the bracket will be Fg for a Poisson structure on A. So given two resurgent series, we can compute their bracket. So it will be pi applied to F times G. So it's what I mean with this wedge product, I simply mean psi times so d of the first factor c delta of the second minus c delta of the first factor del of the second. So that's the first statement. Second statement, let's do it with, well, let's play with the graded algebra. Suppose we have psi dot. Psi dot is a trans series. Non-zero. And C again is a scalar alternal family. And now the support condition is that for every integer m, the elements of the support with some m, so this is finite. So maybe the support is infinite. I mean, because now we will consider, the goal is to be able to consider this sum with the dotted operators. Dotted operators meaning, well, you take the product in reverse order of these dotted elements, dotted derivations. So I want to be able to consider that, but in my graded algebra, I have the grading. So this has grading sum of omega. So I just need that in each homogeneity M, I have at most finitely many elements, and it will be empty if M is negative, so that it's really an operator inside that graded algebra. So that's the condition. Then what is my Poisson bivector? It's this wedge, del and psi dot in front. So this is a Poisson structure on my graded algebra. Non-trivial. Non-trivial because I suppose the coefficients are non-trivial. So you see the natural notation here is C delta dot. And the last statement. So here we have a Poisson structure depending on M, psi, C. And here it depends on psi dot and C. So now the last statement is that for each of these, but in the first case, I take M equals 0. So in A, if I want to stay at the level of series, I need M equal 0. But for the other ones, I don't need anything. And the claim is that there is a star product. There exists a non-commutative associative star product. So let me denote it F star TG. So T will be the deformation parameter, such that at first order, we recover the Poisson bivector, the Poisson structure. So that's the statement. And the proof is terribly easy of the last statement thanks to Maxim's explicit universal formula, because, so can I say in 2 minutes the ideas behind the proof? I mean, the outcome, the message is that we have plenty of non-commutative deformations of the algebra of resurgent series or resurgent trans series, although we are dealing with series in one variable. Plenty, because you have all these derivations available. So the first part is really easy algebra manipulating. I mean, what is the difficulty? Jacobi identity. I mean, a Poisson structure is something antisymmetric. Well, I have the wedge here. It's moreover, it must be a derivation with respect to each argument. So when you fix f, you see that you get psi df times c, this derivation acting, minus psi c delta f acting, and then you have del acting. So this is a derivation for every f. So the only trouble is to prove the Jacobi identity. So you look at the Schouten bracket, and in my computations, I observe that if we are in that case, or that one, it works. You could try to conceive more general Poisson structures. I'm not saying these are all of them, far from it. I don't know. Maybe I can show you one formula which helps to understand what happens. It's something about the commutator. You see, all our Poisson bivectors are of the form, we can write them in this way, where d0 is d over dz, and psi1, d1 is psi times c delta. And in the Schouten bracket, you will observe that you need the commutator. But here I have fixed things so that this commutator is, in the first case, you find d psi over psi plus m multiplied by d1. It's proportional to d1. So, and in the Schouten bracket, you have a wedge of 3 guys. And the third guy is a combination of the first two, so it's 0. And that's it. And in the second case, you just have d psi dot over psi dot d1. So it's the same proof. Yes. So from here, when you want to start product, if psi is constant and m is 0, they commute. So really, you see no difference with d over dq and d over dp. So everything you know about that case, so when psi is constant, you can use the Moyal formula. Moyal formula is just the exponential of t over 2 pi tilde, where pi tilde is before making the products. I mean, it's just, this pi is composition of pi tilde with the product. So I'm saying if psi is constant, okay, that's it. And if psi is non-constant, well, nothing prevents you, I think, to use Maxim's formula to define explicitly the star product.
Yeah, but to understand that it's kind of, you have two vector fields, not commutative, but the two-dimensional subbundle will be integrable. And effectively, we reduce the equation in 2 dimensions, and Jacobi formula says automatically, yeah.
Okay, so this you must explain to me, please, because my time is over anyway, so thank you for your attention.
So, questions? Is there a simplest first example?
So the simplest first example would be d wedge commutator of delta minus 1 delta 1. That's a non-trivial derivation commuting with d. I had no time, but when you have a product of dotted alien derivations, dotted, the commutator is, due to that formula, no, sorry. not dotted. I mean, I'm using that form. I mean, dotted ones, they commute, so you don't care. If they are not dotted, you get the sum. So this is why in the case of series and not trans-series, I have this condition on the sum. But here, if I take minus 1, 1, I mean, this is a derivation which commutes with del. So that would be probably the simplest example.
Maybe a naive question. You have this Hopf algebra. Can you characterize what the corresponding algebraic group is?
I don't think there is an algebraic group, but the idea is that the things which behave like derivations, they are primitive. And the things which behave like automorphism, they are group-like. I mean, so here this would be the group-like element. And yes, the exponential. But the funny thing that we do when we use Ecalle's tools, these families, alternal, he called them molds. Molds are just the coordinates on the tensor algebra, in a sense. And alternal molds are connected with primitive elements of a certain Hopf algebra. And then there is another notion, symmetral molds, which corresponds to group-like elements. And symmetral is just the formula that you need. I mean, I said at some point, where is it? Oh, somewhere. Is it here? No, it's the wrong one. Really? Okay. Yes, it's here. Yes. So I asked who among these operators is a derivation? Answer, phi must be alternal. Now I can ask who is an automorphism? Answer, phi must be symmetrical, meaning that this product, this sum, sorry, must not be 0, it must be equal to phi alpha, phi beta. So it's very natural, I mean, and using that, it's quite obvious. So when we say Hopf algebra here, I mean, I don't think there is anything algebraic because it's really infinite dimensional, so I don't know.